Next, we look at minimizing a function subject to a constraint. First, we look at equality constraints. For example, minimize the function f of x equals 3x1 plus 4x2 subject to x1 squared plus x2 squared equals 1. This is the equation of a circle. In this case, g of x is x1 squared plus x2 squared minus 1. So we look at a recipe for doing such minimization problems. First, we formulate what's called a Lagrangian function. So we take the objective function f of x plus a variable mu times the constraint. This mu is called the Lagrange multiplier. So for example, the Lagrangian will be 3x1 plus 4x2 plus mu times x1 squared plus x2 squared minus 1. Next, we set the gradient of the Lagrangian with respect to x equals 0. So the gradient of the Lagrangian with respect to x is dl by dx1, dl by dx2, the two partial derivatives, which for our example is that. So setting that equal to 0 gives us those two equations. Then the third step in the recipe is writing down the constraint itself. So we see that the gradient of the Lagrangian and the constraint together give us three equations in the three unknowns, the decision variables x1, x2, and the Lagrange multipliers mu. We can now solve these three equations in the three unknowns, and if we do so, we get two possible values for the Lagrange multiplier mu, and corresponding to these two values of mu, we get two sets of values for x1 and x2. In many of our examples, Lagrange multipliers will have some kind of physical meaning. For example, in the MATLAB grader problem in the assignment, there will be constraints on the displacement, and the corresponding Lagrange multipliers will have the meaning of reaction forces. Now, this recipe that we talked about gives us necessary conditions. In the previous two videos, we talked about necessary conditions and sufficient conditions. Here we only talk about necessary conditions. You see that we're not talking about the second derivative at all. And the reason is that for constraint problems, the sufficient conditions are more complicated. But when we use solvers, for example, in MATLAB, they will seek to find the minimizer. So we'll kind of skip talking about the sufficient conditions here. So let's see what we just did, the calculation we did, what it means graphically. So in the constraint case, we are looking to minimize f of x, but we can't search everywhere. We are only allowed to search on the circle specified by the constraint. So if we plot lines of constant objective function 3x1 plus 4x2, those lines look like that, and we see that the smallest value of the function is achieved for x1 equals, the smallest value of the function on the circle is achieved for x1 equals minus 3/5 and x2 equals minus 4/5. And that's the point we found corresponding to mu equals plus 5/2. The other point is a maximizer, as we can see in the figure. So I would suggest that you take some time to understand the graphical meaning of the calculation. So what is the motivation? What's the basis for the second step in the recipe that says the gradient of the Lagrangian equals 0? For this, let's plot contours of the objective function, and then let's say that the constraint looks like that. So at a certain point on the constraint, if we plot the gradient of the objective function, the gradient is the direction of steepest increase of the function. And if we plot the gradient, they're not lined up, which means that we can walk along the constraint and still reduce the value of the function. Whereas if we look at a point which is a minimizer, the gradient of the objective function and the gradient of the constraint are lined up, so that there's nowhere we can go on the constraint and reduce the function. And that is the graphical interpretation of the gradient of the Lagrangian equal to 0. So again, we can solve this kind of equality constrained minimization using MATLAB. One way of doing it is using a solver called fmincon. It stands for constrained optimization, constrained minimization. Again, we create an anonymous function for the objective function f, which returns the value of the function and the gradient. Similarly, we create an anonymous function for the constraint, which returns the value of the constraint and the gradient of the constraint, because both the gradient of the function and the gradient of the constraint appear in the gradient of the Lagrangian. Then we set up an options variable that specifies that we will provide the solver with the gradient of the objective function, and we'll also provide the solver with the gradient of the constraint. So we set those two parameters to true. And then we call the solver itself. The solver fmincon is pretty general, and it accepts lots of different forms of constraints. In our case, we only have the one constraint, so all the other arguments are blank, and then the very last argument is the function and the options. And when we solve, we get x, and then this variable lambda is where the Lagrange multipliers are, and we can get the Lagrange multiplier corresponding to the equality constraint by doing lambda dot eq norm length.